everyone and welcome to Science with Sue and CC.
I'm Sue.
And I'm CC, and today we're going to be looking at the muscular and skeletal systems.
Great, so we're going to start with the skeletal system. Now the skeletal system is made up of
Bones.
bones. Lots of bones make up our skeleton. In fact, in adults we have 206 bones, and in a baby, is that more or less? Does a baby have more or less bones than an adult? They do, they have more. They have about 270 bones.
Okay.
They have extra bones, like in a baby when they're first born, you can actually feel the bones in the skull. So there's sort of separate parts to the bone which fuse as an adult. So that's why we end up with less bones. We have a few bones that fuse together by adulthood. So why do we have a skeleton?
To hold us up.
It does indeed, it holds us up. If we didn't have a skeleton, we'd be a little bit like a slug.
Yes.
We'd just sort of be this blob of flesh, which could might be able to move around a bit. But a skeleton is really good for supporting our body.
Yeah.
Yes. And what else does our skeleton do?
It protects some of our organs, like your heart and your brain.
That's right. Our vital organs in particular need protecting. So our skull is a good solid bone that protects our brain.
Yeah.
Our rib cage protects our heart and lungs.
Yeah.
It's all the things that we can't survive without.
Yeah.
Yes. What else?
Your spine protects your spinal cord.
That's another example of protection.
Yeah.
Yes, our vertebral column will protect the spinal cord. That's good. Can you think of something else that our skeleton helps us with?
It helps us move.
It does. It's sort of related to the support. Being supported, it helps us move, but also by having these long bones which act as levers, it helps us move a lot as well. We looked at levers last year, and we can see how having some muscles here and then a long bone means that a little contraction here gives us a lot of movement out here. Yeah, so it's a third-class lever.
Okay.
Yes. Now there are a few other things that our bones do that we don't often think about quite so much, because often we think of our bones as being almost non-living. Whereas bones are not non-living, they're definitely living. They're changing all the time. And some of the things it does, it's actually a reservoir of minerals. So our bones store a lot of minerals that our body needs. It also stores fat.
Oh, yeah.
And it makes blood cells. So all of our red blood cells are produced in our bone marrow.
Okay.
So it has a lot of function for our bones.
Yeah.
Now our skeleton can be divided into two main parts. What we call an axial skeleton, which is the central part, and an appendicular skeleton. And the appendicular skeleton are the limbs. Alright, so our arms and legs. So the central part is comprised of your skull. If we have a look maybe at this one.
Yeah.
We've got the skull, the vertebral column down the back, the pelvis, the rib cage, and the sternum. Oh, and the scapula. All of that central part is the axial skeleton, and then the appendicular skeleton is literally just the limbs. Yep. Right, in front of you you've got a skeleton there, a diagram of a skeleton with lots of little places to write in the names of the different bones. I don't think we're going to go through all of that with you. You've got a list of all the bones to choose from, the names to choose from. See how many of them you can fill in, and then just look at the solutions to fill in the remainder. You don't need to remember all of them, but if you become a little bit familiar with some of the names, some of them you might have heard of before, and sometimes it helps in your communicating with other people if you do know what some of the bones are called.
Yeah.
I hope you've been able to get hold of a chicken wing and a long bone so that you can go on and do a couple of experiments and a dissection, which we'll head into now.
Yeah.
So what makes bones nice and strong? It's that bones, the compact bone, has calcium phosphate in it. Which means that if you try and break, this is a chicken wing bone, try and break it, it is really, really difficult. Now we're going to be dissecting a chicken wing later on in this lesson, so if you want to leave this until you finish dissecting your chicken wing, then you'll be left with a bone that you can try doing this with, and it's really, really difficult. Now if you take the chicken wing that you dissect later on and then put it in vinegar for, well, this one has been in vinegar for actually at least a month. And it doesn't go off because the vinegar is an acid and it acts like a preservative. But the other thing that the vinegar does, being an acid, it dissolves the calcium phosphate in the bone. So this bone is the equivalent of this bone here. And you'll discover that now the bone is completely bendy. I can twist it into a spiral. That's just how it's lost all its strength altogether, and it is completely bendy. And even this thick bone is quite bendy. You can put it into vinegar for a couple of days and you'll find it loses a lot of its strength, but leave it in for a month and you'll end up being able to twist your bone like it's a piece of rope. It's got no strength left in it at all, which is all pretty cool. So that is calcium phosphate, which has been removed. So I have here a long bone which I got from the butcher. It's a femur and it's been sawn in half because that's often how you can get them so that your dogs can have a good chew on them. Very good for their teeth and muscles. So what I'd like you to do is draw first the outside of the bone and some of the features. We're going to have a look at it, the features of the bone from the outside, and then we're going to look at the features of the bone from the inside. And if you draw both aspects in your notebook and label the different parts, that'll be great. And then draw up a table as well with 3 columns, one for the structure, one for what it looks like or the name of the structure, and then one for what the structure is actually like, and then the purpose of that structure. So let's start from the outside. And you'll notice on the end of the bone this lovely smooth cartilage. It's called the articular cartilage. It's very smooth and white, and the purpose of the articular cartilage is to make a nice smooth surface, so to decrease friction, so that when the bones move against each other, they don't rub. So a lack of this sort of articular cartilage results in arthritis, where this breaks down and you end up with bone rubbing against bone. So this sort of bone rubbing against bone, which has a lot of friction and can be very painful. So the cartilage is there to decrease friction. On the outside here, you can see the compact bone, this very hard bone, which if we open it in half, you can see quite clearly here. I'll just clean that off. You can see it's a little thinner here and then it gets quite thick down through here and then thins off again. And that is very hard. That's the stuff that we relate often to being bone, is the compact bone. But there's a lot more to a bone than just the compact bone. So the compact bone is sort of cream and very hard and is there to provide the strength to the bone. All right, inside the bone, you'll find the bone up the top here is quite sort of porous, up there and up here. And that's called the spongy bone. At the end here, you can possibly see where it's been cut in half and you'll notice the redness coming out of there. And this is the spongy bone or cancellous bone. So it's porous, it's a bit like honeycomb, and it's often quite bloody. And that's because it contains red bone marrow. And it's where new bone cells and red blood cells are made. So the bone, we need to remember, is a living tissue. Very often we look at a bone and it looks like it's dead, but it's certainly not. And up here in the spongy bone, this bone is constantly making new bone cells and it's constantly making red blood cells. Now just below the spongy bone, you might be able to see this little line running just through here. It's actually a thin line of cartilage. Through here. It's called the epiphyseal line. So it's a very thin line, and that's actually where growth occurs. So during childhood in particular, when you're growing a lot, this is where new growth occurs. Remember, all the new bone cells are being made here in the spongy bone, and this is where the growth occurs so that the bone can get longer in that epiphyseal line. Now down the inside of the compact bone, we find we have this yellow stuff, which is quite soft. And it's the yellow bone marrow. It's quite fatty. And this, when you're young and growing, was red bone marrow, similar to what's inside the spongy bone here. So it was making new blood cells and new bone cells. But as we move into adulthood, it becomes thick and fatty. But if we were to remove all the bone marrow, then that space in there is called the medullary cavity. So that's hollow. And the reason that our bones are hollow is so that they're lighter. You can imagine if the whole shaft were made of this compact bone, just how heavy our bones would be, which would make it very difficult to move. Very difficult, because you're having to drag around these heavy bones. One more thing I'd just like to show you is over here, where we've got this lovely articular cartilage, we've then got this huge tendon here, which is just delightful. You can see that it's attached down here on the bone. It's very white and smooth and really strong, really, really strong. And that's so that when their large muscles contract it's not going to break, and it's well attached to the outside of the compact bone, and so it's unlikely to ever come off. It can happen. People can have very bad injuries where they do come off, but mostly not. We've got here an x-ray of Cece's foot from a couple of years back, wasn't it?
Yeah.
When she fell over, and you'll have a look at these two metatarsals, and you can see very clearly how they've been snapped in two. So this is a good example of how bones are living, because those bones don't remain broken. Anyone who's broken a bone knows that it doesn't stay that way.
Yeah.
It will actually knit itself together again. Now, a big weight-bearing bone that was broken this badly would need a pin to straighten it up so that it stays straight whilst it mends. Because these aren't weight-bearing, they were actually left the way they were, and because Cece was quite young, they will knit together and then actually straighten themselves up a little bit.
Yeah.
The body is very, very clever, very well designed. Now, some other conditions that can occur with bones, apart from an obvious break, is something called osteoporosis. Have you heard of that? Osteoporosis. It's a condition where the bones become more fragile and they break more easily.
Yeah.
And that's because the calcium in our bones decreases with age, and that's all related to hormones and things. It's also related to vitamin D intake.
Okay.
So a good way to help prevent osteoporosis is to make sure you have plenty of calcium. Where do you get calcium from?
Meat?
Not so much. Milk products.
Oh, of course, dairy.
Yes, dairy. Dairy is something you need to eat to get your calcium. If you can't eat dairy, there are other places to get it, other sources, and you need to look into that if you're not able to eat dairy. But dairy is a really good one for getting your calcium.
Yeah.
Where do you get vitamin D?
Vitamin D from the sun.
Yes, you need to get out and get a bit of sunshine, and your body will actually produce vitamin D. And the other thing that helps strengthen your bones is exercise. So the more you use your muscles, which are pulling on your bones, then the stronger your bones will become.
Yeah.
And so that will also help prevent osteoporosis. Now, there is a genetic predisposition to osteoporosis. That just means that you inherit the tendency to get it. So sometimes you can still help make it better as best as possible, but some people actually don't tend to get it where others do. And there's not much you can do about that. But you can still look after yourself so that you can keep your bones as strong as you can by eating calcium, getting out in the sun to get some vitamin D, and exercising. It's a good way to look after your bones. Now, our bones aren't going to be terribly useful for movement and things unless we have joints.
Yeah.
Now, joints are just where two bones articulate. That means they come together, they join, and they allow movement. Now, when we looked at our long bone, we saw the articular cartilage on the end, how it's very smooth.
Yes.
And that reduces the friction so that we don't get rubbing. Now, there's something else that helps with joints as well. Where the two bones come together, not only have you got a smooth surface, but within there's usually a capsule around the joint, and there's fluid inside.
Yeah.
So it's a little bit like oil. It's called synovial fluid, and it's like oil that lubricates the joint.
Yeah.
So again, there's not much friction, which is good. And then you've got the ligaments within the joint that actually join the two bones together and keep the joint stable.
Yeah.
All right, now there are lots of different types of joints in your body, and different joints allow different sort of movement. So we're just going to look at a few. We've got 5 here listed.
Okay.
A ball and socket joint. Where do you find that's where you've got end of a bone like this, and then the next bone is a bit like this. Where do we find ball and socket joints?
In your shoulder.
Yes.
And in your hip.
In your hip, that's right. And we looked at those last week when we put the organs together. We had the femur and the humerus, and we saw the ball at the end of the bone. So it's a ball and a socket, and the good thing about that is that it allows lots of movement.
Yes.
So if you have a look at your arm
You can twist
and
around.
see all the different movements you can achieve, you can flex at your shoulder, you can extend at your shoulder, you can move it outwards, which is called adduct, or abduct and adduct your shoulder. So move it out and in. You can also move it right around.
Yeah.
Yeah, so you've got lots of movement in your shoulder. You've got similar movement in your hip, it's just not. The hip joint has a bigger socket because it needs to be more stable. It's holding your whole body weight, where your shoulder doesn't have to, unless you're doing handstands, doesn't have to hold your body weight. But as a result, your shoulder can dislocate more easily than a hip joint. And you very possibly know somebody who's dislocated their shoulder, because that's fairly easily done because the socket's very small. Some hinge joints. So a hinge joint is just like the hinge on a door. Right, can you think of anywhere in your body where you've got some hinge joints that just, okay, if we think about a door just opens and closes.
Yeah.
That's about all it can do. What are some joints that can only do that?
So you've got your elbow.
That's right,
Yeah.
your elbow is a hinge joint. It can only go up and down.
Fingers.
Yes, between the
Yeah.
phalanges of your fingers.
Yeah.
That's all it allows.
And your knees.
Yes, your knee is exactly the same, well not
And,
exactly, but very similar to your
yes,
elbow.
And your toes.
Okay, the phalanges in your toes as well. Excellent, there are a few examples. So they just allow, flexion and extension. So to flex means to make the angle smaller, and to extend means to make the angle bigger.
Yeah.
All right, a pivot joint. There's really only one place in your body that we have a pivot joint, and that's between the atlas and the axis. Do you know where the atlas and the axis is?
I'm not sure.
It's the first two vertebrae in your neck.
Oh, okay.
Right, so you've got a little process sticking up and then another bone that sits on top of it, and it allows you to go like this, which is this movement
Yeah.
of your head. And it's really the only place in your body where you get that movement. It's a pivoting movement. So you can just look right around, rotation movement. Now a saddle joint, that's a very special joint found in the human body, and it's in the thumb. Right, and it's this joint in the thumb that allows our thumb to move differently to all our fingers.
Yeah.
Because our fingers can only flex and extend,
Yeah.
but our thumb can actually move right across.
Mm.
And it doesn't just flex and extend. And humans are pretty special like that. And it means that we can get what we call a precision grip. We're able to touch the tips of every one of our fingers, which means we
yeah.
can pick up very small things. If you've ever tried to live without a thumb, you'll realise how difficult
Very
it is to
difficult.
pick things up. That could be a little experiment to do, is actually tape your thumb to your hand and try doing your normal everyday activities without a thumb for a while. And you'll find just how much we rely on our thumbs.
Yeah.
And that's because of that special thumb saddle joint in our thumb. And a fibrous joint, we've actually already talked about. A fibrous joint is where two bones sort of join, well, they become quite fibrous, they join together like this.
Okay.
And then there's actually no movement. It's a very solid joint. Do you remember
Okay.
where we talked about that?
Is that in the skull?
That's right,
Yeah.
in the skull, because when a baby's born, we've got a number of bones which then join together, they fuse together as a fibrous joint,
Yeah.
where there's no movement. So by having them as separate bones, to begin with, it allows for the growth, but once growth is finished, it provides a nice strong protection where you don't actually want movement.
Yeah.
Yeah. All right, now we talked about bones being alive. We didn't talk about the cells that are being made. There are osteoblasts, which are the cells, the bone cells that are constantly being produced by the bone,
Yeah.
which makes new bone. And then there are osteoclasts, which are another sort of cell that's produced by the bone, which removes old bone.
Yeah.
So in fact, new bone is being produced all the time and old bone is being removed.
Yeah.
So it's a living, that's why broken bones can heal, and it's a living organ just like all the other organs in our body. And now we're going to move on to the muscular system. So this lesson is a little bit long, but the muscular system is short enough that we've put these together, or we're going to take a whole term just doing all our systems.
Yeah.
There's lots to learn about the human body, which is fun. But next week is a little bit shorter. So if you want to stop here and pick this up again later, that's probably a good place to stop. So the muscular system is very closely related to the skeletal system, and that's
Yeah.
why we're putting them together. But the muscular system isn't going to do very much if you don't have a skeletal system for it to attach to.
Yeah.
So we need some bones for the muscles to then move, and it allows the movement that we need. So muscles, particularly skeletal muscles, are often found in antagonistic pairs. So an antagonistic pair is like last week when we put the biceps with the triceps. Yeah, they're a pair of muscles that are on opposite sides of the bone. So when the biceps contract, can you just put your arm out for me? When this muscle contracts, it's going to pull your arm up.
Yes.
But if this muscle on the back is also contracting, you're going to have trouble.
Yeah.
So the triceps on the back, when you do that, needs to relax. Now, to straighten your arm, you need the triceps to contract, and that contracts and opens your arm up.
Yes.
But if this muscle doesn't relax, again, you're going to have trouble. So these are antagonistic pairs, the biceps and the triceps. One contracts, the other relaxes.
Yeah.
Then the other one contracts, and this one relaxes. And that's how you get movement across joints.
Yeah.
And then, of course, your muscles are attached to the bones. The muscles are going to be useless if they're not attached.
Yeah.
And they're attached by tendons. We looked at tendons when we were looking at tissues. And the important thing about tendons, is up this way again, is that the muscle is here. The tendon needs to join the muscle across to the next bone. Otherwise, if it was joined onto this bone, when it contracted, nothing would happen.
Yes.
So it's got to be joined onto the next bone. And that's why the tendons are really quite required, because they're a strong, thin piece of tissue that can go through the joint nice and thinly. In fact, if you just bend your elbow, you can feel the tendons in here.
Yes.
Yeah, moving across the joints. You can feel tendons all over the place. We felt them in the back of our knees earlier. And the best way now to look at how these antagonistic muscles appear is to dissect a chicken wing. So off we go to do that.
Okay.
Now we're going to dissect a chicken wing. Now your chicken wing is the forearm of the bird, of the chicken. So it's very similar to our upper arm. So in this section we'll find a single bone, like your humerus, and then 2 bones down in this section, like the radius and ulna, and this section is much like your hand. So it's made up of a number of different bones. To begin your dissection, you start by cutting off all the skin. So if you remember from our last dissection, you lift, slide in your scissors and snip down the length of the skin. And this is where forceps with teeth on it can be very handy. Now in here you may find, like I have, that you've got some blood vessels in there full of blood, which is quite nice to have a look at. So here we have, and you might be better using something a little less teeth to try and grab that. And there's a nice artery running right under the skin there, which I'm going to try and separate from the surrounding tissues. Most vessels and anything is actually just attached with connective tissue. So they're not just floating around loose, but they're held in place just by some connective tissue. But if you very carefully just try and snip through that, you'll find you're able to lift out lots of different vessels. Yeah, and you get a feel for just how strong the arteries are, much stronger than the veins. All right, now I'll continue to remove the skin. So you need to be patient in doing this, because otherwise you can end up cutting a lot of the tissue underneath, which you don't want to do. You want to try and keep it all in one piece. Just before I go any further, I'd like to have a look at the joints that we've got. So remembering this is like your humerus, your upper arm, then this is like your elbow. And at that joint you can flex and you can extend. And then we come down and this is like your wrist, which again can flex and extend. I'm just going to finish taking off the rest of this bit of skin, but you can leave the skin that's on the last little bit. That gets a little bit, it's attached very tightly and can be difficult to get off. So now we have the chicken wing with most of the skin removed. So you'll notice with muscles, they're very often paired up in what we call antagonistic pairs. So like we looked earlier at our biceps and our triceps, the biceps on the top of the arm is equivalent to this one. So it's a large belly muscle with a tendon that goes across the joint. When that muscle contracts, it's going to pull this bone up towards it. So when it's lengthened, this can be out, but when it contracts, this becomes shorter, which pulls this part up and so flexes this joint. Now on the opposite side, there's the equivalent of the triceps, a muscle on the other side. So when the biceps is contracting, the muscle on the other side needs to relax so that it can stretch, become longer, so that this joint can flex like that. Now, once it's flexed, the opposite happens. This muscle contracts and gets shorter, and because it's got a tendon that goes around the joint here and attaches to this bone, when it gets shorter, then it automatically pulls this and extends that joint so that it's straight. But in order for it to do it, this muscle must relax, because if this muscle stays contracted, they're then fighting against each other. So that's called an antagonistic pair. As one contracts, the other one must relax, and then as this one contracts, this one must relax to do the opposite movement, like that. Now I'd like you to have a look at some of the muscles. Have a look at the tendons at the end of the muscles, which we did look at the other day when we dissected a drumstick. But I'd like you to have a good look inside this joint once you've removed some of the muscles, and have a look at the ligaments that join the joint together. So remember, tendons join the muscle onto the bone. Ligaments look very similar, but they join bone to bone. So remember, you can separate muscles just with your fingers, and that helps you to separate out the bellies of the muscles. And here we can see a nice clear tendon at the bottom of the muscle that then joins onto the bone. And the tendon will always go across a joint, because a muscle here is useless if it joins onto the bone in the same section. The tendon is that nice thin strong part which goes across the joint so that the muscle can actually make some movement at that joint. And as I move this joint, you can see what's happening to this muscle. You can see how this tendon gets pulled around. So when this is flexed, when this joint is doing this muscle must be relaxed to be long. When this muscle contracts, then it's going to pull that up. So if we start off with that flexed, you can actually just grab this muscle and contract it manually. So if you give that muscle a pull, it will flex it out. Now, remembering this joint is your elbow, if you can find what's the equivalent of the biceps, you should find that by, try and do this so you can see, pulling that muscle, you can see that it flexes that joint. So it flexes the elbow just by pulling the muscle. So when the muscle contracts, that's the effect it has. It's joined on by a tendon across that joint, across the elbow joint. And then your triceps is on the other side. And so if we pull that, it will extend. So that's an antagonistic pair. One flexes, the other one extends. So you see if you can find yourself an antagonistic pair of muscles, where you pull one, it will flex the joint, and when you pull the other, it flexes, it extends it. So flex and extend, flex and extend. And that's how your muscles work over the joints. Now we're going to continue to remove all the muscles so that we can have a look within the joint and find some ligaments. So here we have a wing where the muscles have been removed, and if you look, get right into a joint and find what looks like a tendon, but you'll discover that the tendon, here's one, like this, it looks like a tendon, but it's actually just going from this bone to this bone. It's not joining onto any muscle. And if it's going from bone to bone, then it is a ligament. So the ligaments are much like tendons. They're a strong connective tissue that just hold the joints together so that the bones don't slip apart. So that's a ligament there. I'm sure you'll be able to find some others. If you're dissecting a chicken drumstick, sometimes you can see the ligaments, depending how the butcher's cut the drumstick. If you've got a little bit of the next bone left on, you can sometimes see the ligaments joining the articular cartilage together. Now, interesting thing here, this particular wing has all the articular cartilage in contact, it's complete, whereas this one has had the end cut off. So this is the outside of the articular cartilage, and inside you can see the spongy bone there. that birds also have. Similar to the long bone that we looked at with the articular cartilage. Now, I'd like you to have a go at breaking one of the bones, or all of the bones for that matter. Just have a go. Maybe you start with the finest bone and see whether you can break it, which I have, and you'll notice inside that it's quite hollow and it's also red, so you've got the red bone marrow inside there where it's producing red blood cells. And then try the next larger one and see if you can break that, which I am absolutely not capable of doing. And so then getting on to the next one, there'll be very little hope of breaking that, at least for me. Now, chicken bones and bird bones in general are usually much thinner. The compact bone is much thinner than terrestrial animals. The compact bone can be quite thick, and there's a good reason for that. That's because birds need to be able to fly. They've got to get their whole body weight off the ground. And if their bones are very heavy, that's going to be very difficult. So bird bones are more fragile than terrestrial animals, the bones of terrestrial animals, which can get away with having thicker, compact bones. Now, I've just pulled this joint apart quite roughly, and inside you can now see this ligament. It's clearly joining this part of the bone to this part of the bone, and therefore it is a ligament, it's not a tendon. And that's really the only way you can tell the difference between ligaments and tendons at first observation, is just to see where they're attached. And there's another one down here, joining from bone to bone. So they're the ligaments that hold the joints together. And now we have an activity to finish off with, where we look at muscle fatigue. I'm sure you've all experienced using your muscles and they gradually become tired and even sore. Yeah. If you use your muscles a lot like if you go for a sprint, you'll find that your muscles actually aren't able to get enough oxygen to keep working, and they go into what we call an anaerobic respiration. Okay. So that's a way of respiring that doesn't use oxygen, but what it does do is produce lactic acid. Mm-hmm. Yeah, it doesn't just produce carbon dioxide, it produces lactic acid, which can build up in your muscles, and that's where you need to cool down slowly to try and remove some of that. And if you have a lot of it in your muscles, then you can end up quite stiff the next day. Mm. Yeah, I'm sure we've all experienced that. All right, but we're going to just do a little investigation to see how fatigue in muscles affects how fast we can use our muscles. Okay. So you'll need two people to do this activity, one to hold the timer and one to do the stepping. So I'll do the timing and you can do the stepping. Yeah. So I start the timer, and for 30 seconds, CC is going to step up and down as fast as you can. You need to count how many times you're stepping. Okay. In the 30. I'll tell you when 30 seconds is up, and I will record the results, because you need to keep stepping. You don't stop, you just keep stepping. And when I get to 30 seconds, you need to start. You tell me how many you've done, and then you start counting again. Keep going again. No, you start counting from zero, from one again. All right, so off we go. All right, ready, set, go. Another way you can do this is to use a peg, or a large peg, because the problem that can arise with using a step is that you actually get puffed out before your muscles fatigue. Do something like this, you don't get puffed out, but your muscles still get fatigued. Yeah. But you may not have one of these at home. However, we're going to do it with this right now. So let's see, I'm going to start the stopwatch. If you count out loud, then I'll know what number you're up to. I'll tell you when it's 30 seconds. Maybe I'll just say, start again. And so then I'll be ready for the next 30 seconds. So you start counting again. All right. All right? All right, because this can be quite fast, what I'm going to do is keep a tally of every time CC gets to 10, so that she can just start counting from 10 again, rather than trying to say 73, 74, 75 when her fingers are going too fast. And then I'll just say start again. All right. Ready, set, go.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 7, 8, 9, 10.
Stop.
1, 2. Oh my gosh!
How does your thumb feel?
Painful.
Where does it?
Thumb area.
So,
Sort of down here.
in your forearm as well?
Yeah,
Or
about
mostly-
mainly in my thumb, but yeah, a little bit down here.
Okay, because you're using muscles all the way up your
Yeah.
forearm as well as in your thumb. Well done. Good.
Oh.
Now we can graph those results. Now, as with all experiments, it's good to not just do it once. So we do it more than once. If you've got doing it with a friend or a sibling, then make sure that you get them to do it as well. And you can have 2 or 3 or even 4 different sets of results and get an average from those, which will be more reliable.
Yeah.
Okay. Now, in this experiment, what is our independent variable? First, what is our independent variable generally? Is it the one we change or the one we measure?
It's the one that you change.
It's the one that we change. So, what are we changing in this instance?
Time? No.
Yeah, no, it is the time. It's a little bit tricky. It's because we're doing it for the first 30 seconds versus the second 30 seconds
Exactly, yeah.
versus the third 30 seconds. So it's time that we're changing. And what's our dependent variable? What is it that we're measuring for this experiment?
Time.
No.
No?
No. The time we changed, first, second and third. But then we're counting. What is it
Oh,
we're
how
counting?
many steps we've done.
That's right.
Right.
So we're measuring how many
Oh.
steps. We're counting how many steps you manage to fit into each block of 30
Yeah.
seconds. All right, so if we're going to graph these results, is time quantitative or qualitative?
Quantitative.
It's quantitative, we can measure it. What about the number of steps? Is that quantitative or qualitative?
Quantitative.
Again, we can count it, it's continuous. So if we've got 2 quantitative variables, what sort of graph should we be having?
Line graph.
That's right, a line graph. All right, if we have one that's qualitative, then it's a bar graph. But we can make a line graph of this. So that's really good. Once your results are recorded and you've done an average, you can then draw up a line graph of your results. Make sure it's got a title, that the axes are labelled,
Yeah.
that you've got a nice even spacing of your scales on the X and Y axis. Yep. And then you can look at your graph and tell us what happened as time progressed. All right, each 30 seconds, what happened? Did you manage to get more steps or less steps?
Less.
Less. Less. It did. It became harder to go as fast as the time progressed. And why do you think that is?
Got more tired.
Okay. Could you feel it in your muscles? Did your muscles get more
Yes.
sore?
Yeah.
Yeah, your muscles get tired and sore. And it says, but different people actually get different results, don't they? And why do you think that is? Why do some people manage to go longer and some people tire out much more quickly?
Because their muscles are used to it. They've trained.
Okay, training and using your muscles actually makes them work more efficiently.
Yeah.
And they're able to put up, they don't get fatigued as quickly and as easily. So it's good to keep your muscles nice and strong
Yeah.
and to use them. Yeah, and then they'll be able to work for you better. The last thing to do for today is to add to your flip chart. So you've done your cover, which looked at the skin.
Yeah.
Now if you can find an example of a skeleton, blow it up to be about the same size as just the outline of your body, and then trace. You don't have to trace every single bone, but do the best you can at drawing some of the bones and then do another page with some of the muscles. Again, you don't need to know every muscle in your body, but it can be fun to try and choose muscles that you like the sound of. I love gastrocnemius. I always remember learning that at university, and that's your calf muscle. So if there are any names that you like, use those ones, or just choose ones that sound familiar. Ones that get used a lot, like the deltoid, the biceps, the triceps.
Yeah.
Ones that people talk about are the ones probably best to fill in. But don't get too hung up in trying to learn all the names. Oh, well, that's all for today, and we will see you next week.
Bye.
Into two. No, I'm going to do that again. I'm trying to work out how to bring it in.